Greetings, my name is Ferrino Abuda from Kumo National Institute of Technology, and today I will be discussing about GPU allocation based on resource consumption. Nowadays, deep learning is widely used in fields such as natural language processing and computer vision. As time progresses, deep learning models continue to grow in layers and parameters, which creates increased complexity and also, in turn, increases training time. And due to these two factors, it also increases the hardware demands for training such models. On the right side, we have commonly known convolutional neural network models, such as VGG, GoogleNet, and ResNet, which can also vary in complexity depending on the amount of convolutional layers configured. Next will be the objectives of the paper. So we aim to maximize the utilization of available GPU hardware resource, which we believe will also reduce the training costs, since higher efficiency will lead to lower training time. We also try to determine which GPU should a given training workload should be allocated. So in order to achieve these objectives, we aim to focus on GPU memory utilization percent and GPU utilization percent. So to begin with our framework, we have four major blocks found here. First, we try to start training a CNN model using two different datasets, such as Cypher10 and ImageNet. Running in parallel is the data gathering for GPU memory utilization and GPU utilization percent. So this data gathering is calculated at a rate of 1/6 per second. Once we are done with training, we'll then convert this data into idle time, burst time, and peak consumption rate in order to create a data set. So this data set will then serve as an input for our prediction model called DRIPO, which was created by a previous author, which will give us predicted values for these three parameters: idle time, burst time, and peak consumption rate. And based on these predicted values, we will calculate the efficiency of each GPU and determine GPU allocation. So how do we define burst time, idle time, and peak consumption rate? So we define burst time as greater than or equal to 50% of maximum output, idle time as the opposite of burst time, which is less than 50% of maximum output. So to begin with, on the gathered data for GPU utilization percent and GPU memory, we set a boundary at the middle defined by this black dotted line, and then we separate the data into two classes using k-means distribution. So on the right side of this boundary will be the burst time data points, and on the left side will be the idle time data points. Lastly, we have the peak consumption rate, which is 90% of maximum output, which is defined by this red dotted line. And the peak consumption rate data points are defined by the data found on the right side of this boundary for both graphs. So for our experimental setup, we'll be using two datasets, ImageNet and Cypher10, using Adam and SGD optimizers with multiple batch size configurations, A16, 32, 64, and between two epochs, which is 10 and 20, and using various ImageNet models and various Cypher10 models. So we will be creating a sample for each combination in this hyperparameter settings table, which will give us up to 240 samples. So as as to visualize the configuration, we have a sample here, which is using ImageNet dataset, and we will be using Adam optimizer, which with batch size 32 and with the setup of 10 epochs on the VGG11 model. So this counts as a single sample, and we have 240 samples for each dataset. So for this experiment as well, we will be using 3 different GPUs, which is Titan X, RTX 2070, and GTX 1080. For the software, we will be using TensorFlow 2.5 and CUDA 11.2. So for the evaluation, first we state the available memory for the GTX 1080 and RTX 2070 to be 8 gigabytes and Titan X to be 12 gigabytes. Also, we have on our experiments, we have observed CPU bottleneck on RTX 2070. So as shown on the table below, here we will see the average GPU utilization and GPU memory utilization for each model with respect to each dataset. So we can observe this CPU bottleneck on the part on training ImageNet models on the RTX 2070. So we have blank entries here because we were unable to obtain sufficient data for the configurations for each model. That's why we just prompted to put in a blank entry due to the CPU bottleneck. So in order to further visualize this bottleneck issue, we can compare the VGG11 model for the 3 GPUs, and we can see that it's quite similar to the GTX 1080, and Titan X has similar GPU utilization. However, we can see that for RTX 2070, there's a massive drop in GPU utilization due to the CPU bottleneck issue. So going further, once we finish gathering the GPU utilization and GPU memory utilization, we now convert the gathered data into burst time, idle time, and peak consumption using the defined criteria as previously mentioned. Now we try to compare burst time and peak consumption for 3 GPUs using similar models between different datasets. So here we can observe for table 3 that AlexNet model has higher burst time for Titan X on ImageNet and GTX for Cypher 10. However, for RTX 2070, it has the highest burst time ratio for the trivial model. On the other hand, for peak consumption, we can see that GTX 1080 has higher peak consumption for ImageNet dataset, while Titan X has higher peak consumption for Cypher 10. However, we can see here that, as mentioned previously, because of the nature of the CPU bottleneck, it also affects the peak consumption rate on the RTX 2070, and we have very low values on the peak consumption rate for RTX 2070 compared to the other 2 GPUs. So once we are able to obtain the burst, idle, and peak consumption rate, we then use it to create a dataset. And once that dataset is created, it will serve as an input on the dripple model to get the predicted values. So for the predicted values of GPU resource usage, we have two tables for each GPU resource, which is GPU memory utilization and GPU utilization percent. Here we can see that the burst time is highest for GTX 1080 and peak consumption is highest for Titan X. However, for GPU utilization percent, it is highest for GTX 1080 for both burst time and peak consumption. So once we have these predicted values, we now try to calculate the GPU efficiency based on the burst and peak consumption rate. We propose this formula, which is the GPU efficiency is equal to average peak over the average burst, which will give us the score as shown on table 8, which is the GPU efficiency per GPU resource type. So we can see here that GTX 1080 has the highest score for GPU utilization, but Titan X has the highest score for GPU memory utilization. However, when we are trying to allocate based on GPU efficiency, we will try to combine these uh, scores together, and GTX 1080 obtains a higher total score than Titan X, which also means that when allocating tasks similar to the models and data sets used on this work, the GTX 1080 should always be the first option, while Titan X will be the second closest option. And RTX 2070, we can see here that the scores are really low due to the bottleneck issue that we have encountered. So what are the key points for this research paper? We have encountered that hardware bottlenecks can occur, such as the CPU bottleneck, and we were able to estimate the GPU usage efficiency through smaller iterations, which means we do not need to train over 100 epochs in order to get the usage efficiency of training a neural network model. And next we have the efficiency score. When we utilize the efficiency score of a GPU, it can lead to lower training costs. And lastly, to address the bottleneck issue that we have encountered, future work will also consider GPU usage, CPU usage, and wall clock execution time in order to determine how does CPU and wall clock execution time actually affect the training efficiency of neural network models. Thank you for listening, and that's it for my presentation.